So just hang in there. You guys are the strong ones.
It's actually,
Or the slightly less weak.
I like the math-heavy chapters because it makes more sense for my brain. The more conceptual stuff is the harder stuff for me.
Yeah, Gen Chem is pretty awkward. And then I will say, so if you don't like the math, and that's how some people say, like they hate the first quarter because it's too much crap, but then they love the math later, and then other people obviously feel the exact opposite. But then if you look at the syllabus, we'll get into more fun stuff again, transition metal chemistry, OChem, towards the end, so kind of back to the molecules and not just math. So just, again, hang with it, ask me for help. I have not seen people this quarter in my office hours, but I would love to see y'all and all that. Oh, and then just a reminder for Earth Day. So, of course, Earth Day then we'll have the presentations. So if you can come, again, Dusty will be there kind of checking who's there, and he'll be me. And if you can't make it to Earth Days, just leave your finished product in the lab room. So I'm planning on just leaving it in HEC 312 so you can have them set up there. So ideally you're finished by Thursday lab session. If you need to finish up last minute things, I'd say have them, done by Friday. And then when I get back from my conference, I can grade them probably like Monday, look at your projects.
Isn't Earth Day next week?
No, Earth Day is this week.
Oh, okay.
Yeah, the official Earth Day is on Saturday. And look around in your community too for events. I know they're doing like the Greenway cleanup. The library's having some Earth Day stuff. So fun times. All right, we should dive into lecture because like I said, there's going to be a fire alarm at 1, and I'm going to try to get through a lot of this chapter. All right. So let's think back. Oh, this is not where we want to start. I'm sorry. All right, so let's start here with thermodynamics and spontaneity. And so now we've been looking at kind of reactions in a lot of different ways. So we started back, if we think back to enthalpy, so we were comparing endothermic and exothermic reactions. And then we kind of got into how fast with chemical kinetics. And so now we're answering, well, is a process spontaneous or not? And so thermodynamics tells us whether a process will occur under given conditions. And so processes that will occur are called spontaneous, so they happen. And then non-spontaneous processes require some sort of energy input. And so spontaneity is determined by comparing the chemical potential energy of the system before the reaction with the free energy of the system after the reaction. And so if the system after the reaction has less potential energy than the system before the reaction is thermodynamically favorable. And so, right, spontaneity, again, has nothing to do with how fast or slow, so we address that in chemical kinetics. So again, we'd have to go back to kinetics and measure the reaction rate so we know how to do that. And so, for example, one process that is spontaneous, but obviously does not occur very quickly or else people would not buy diamonds. But so on a very long time scale, diamonds will spontaneously decompose back to graphite. And so this is, again, just the thermodynamically favorable sink here of graphite. So molecules tend to want to go to what's the lowest in energy, most thermodynamically favorable. And so while this process is spontaneous, meaning we don't have to put any energy into this process, it obviously occurs at a super slow rate.
What's the half-life of diamond? That's a serious question.
I would have to look that up.
Does that mean all of diamond rings are just going to be chunks of pencil?
Eventually,
What, that was
yes.
fun? You put diamond in a nearly pure oxygen environment and heat it up, you can burn them.
So then we have what's called a reversibility of a process. So any spontaneous process is irreversible then, because there is a net direction of energy when it proceeds in that direction. And so we can think of spontaneous processes like your car is going to rust, unfortunately, right? It's not going to go the other way, right? You never see a rusted car become new again just sitting there. So same thing with like cooking, like scrambled eggs, right? Once you scramble those eggs, you can't unscramble them back to yolk and their components.
Isn't that ignoring like pockets of randomness, let's say, that can make things go backwards?
No, I mean, in no way can rust go back to here. Like, you would have to put some sort of energy in, like, electrolysis, electroplating.
Yeah,
So you would have
pockets
to
of
do.
energy could do that.
Oh, we're talking about spontaneously, naturally occurring. So now you're talking about inputting energy, so that's changing something already. So you're talking about different conditions here because you're doing something to it. Spontaneous means you're not doing anything to it. And so a reversible process will proceed back and forth between the two conditions. So we looked at equilibrium. And so any reverse process is at equilibrium, a reversible process. So we've kind of seen that before. And so this results in no change in free energy. And so if a process is spontaneous in one direction, it must be non-spontaneous in the opposite. And so this kind of brings us back at least to a surface level with enthalpy. And so spontaneous processes occur because they release energy from the system. And so most spontaneous processes proceed from a system of higher energy potential to a system at lower energy potential. And so we looked at those mainly with exothermic reactions, right? How we said those are generally favorable. And then obviously we knew they were exothermic since they got hot, so they were releasing heat. And then that's showing us, again, that our reactants are higher in energy than our products. So then we get that, again, your delta H that we've been familiar with released. And so the kind of conundrum with that is, well, there is still some spontaneous process, though, that proceed from a system of lower potential energy to a system at higher potential energy. And so one example of that is going to be barium hydroxide reacting with ammonium chloride. So this is what's in an ice pack, or can be what's in an ice pack. And so if you mix these two together, then it is extremely cold. And so that would be an endothermic reaction, except it occurs spontaneously. So what this is telling us is, well, there's something else that we have to think about that, again, drives whether a process is spontaneous or not, other than just enthalpy. So again, previously we've just looked at enthalpy of whether it's going to go exothermic versus endothermic. But now we're saying, well, there's something else that's dictating this as well. So some other factor that we have to look at. And so now this brings us to what factors do affect whether a reaction is spontaneous. And so like we mentioned, we've looked at enthalpy change before, so our delta H. And so again, that's just the difference between the sum of the internal energy and the pressure volume work energy. And we said for us, right, usually we ignore the pressure volume because usually we don't have a change in pressure volume with most reactions. But now we're introducing in this chapter this new concept called entropy, which is going to be indicated by this delta S. And so that's going to be the difference between randomness of the reactants and that of the product. So entropy is basically order versus disorder, and we'll look into that obviously in this chapter. And so just a quick refresher so we remember to our enthalpy. So recall enthalpy delta H, we measure that in generally kilojoules per mole. And we said a reaction was generally exothermic if the bonds in the product are stronger than the bonds in the reactant. So stronger bonds, more stable molecules. Exothermic is energy released. And again, that meant that our delta H would be negative. And of course, we remember if something is endothermic, the bonds in the product are weaker, so it requires energy, so energy absorbed, and our delta H is positive. Yeah.
So spontaneous things don't occur naturally, is the idea? Why is
Spontaneous things occur naturally.
Yeah, okay. Diamonds turn into graphene spontaneously?
Yes, and I did look up the rate for you. So apparently it would take about 1 billion years to convert 1 cubic centimeter of diamond to graphite, so.
Wow. That's not what I was going to ask. I was going to ask, diamonds are created naturally through natural processes.
Well,
Why is that not considered spontaneous?
they're created, though, through a bunch of pressure and heat, so that's going to be endothermic, where you're adding energy to it, so it's not just like a spontaneously occurring process.
So naturally, is it like, what, net zero energy in the environment? Is that the idea?
It's more that if you just leave something alone, it will just do it, and it will still do the reaction. Like, you don't really have to do.
I mean, what defines leave it alone, though? Are we talking about, like, room temperature? Are we talking about, like...
Yeah, essentially. So you're just leaving it ambient conditions, right, while a diamond is not under those ambient conditions. It's under extremely high temperatures and pressures, and that's how they can create, right, synthetic diamonds really quickly in the lab now. It's just by simulating those high temps and pressures.
Whereas if you just leave a piece of metal out in the rain, it will start to oxidize. And you're not really putting any energy in that, just the right chemical conditions.
All right, so let's continue on with entropy. So entropy then is our thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. And so that's just saying basically you have different systems and then you can arrange them different ways. And so entropy generally, it's in units of joules per mole, so if you look up standard tables, just watch for that. And then entropy can also be related to this Boltzmann's constant, and so this is just K is our Boltzmann constant. You probably won't need this. And then W is just the number of energetically equivalent ways a system can exist, except this W would obviously get complicated really quickly. So if we just look at some examples of what we're kind of saying with W. So if we take, right, 2 molecules, molecules 1 and 2, so we have a little stopcock here. And let's say we open the stopcock so that they can, I guess, mix. And so then you can have 2 possible scenarios. And again, this is literally with 2 molecules. So you could have 1 and 2 over here, or 2 and 1. Right, so now we're already looking at different ways. And so if we were to do the same thing now with 4 particles, so 1, 2, 3, 4, then we open it up, right? And then we can have all sorts of combinations.
So it's a matrix.
So, 1, 2, 3, 4, and we could go crazy with this, right? 1, 3, 4, 2, do the opposite, right? 2, 1, or, sorry, that's not what I put 4 and 3 here, 1 and 2, so keep going, right? So we could, this is already getting out of hand. etc. So we could also make combinations where there's like 3 in 1 and blah, blah, blah.
So the number of possibilities is equal to the square of the number of molecules.
Yes, but then, right, obviously this gets complicated extremely quickly, especially when we're talking about, you know, moles of things. And so other examples then of entropy, and so we'll look at other ways to quantify this. And so of course salt dissolving in water, so that's also a process that's spontaneous but also results in an increase in entropy. So you can see the increase in entropy. So it started off as one ordered block of sodium chloride. Then you dissolved it, and it became, of course, dissolved. So there it is, surrounded by your water molecules. And so that increases the entropy. So that's interesting. And then evaporation is also a spontaneous process. And so that's interesting as well. And increasing entropy, so again, you have your liquid, water, and then as it goes to the gas state, obviously more movement, more freedom, and so that's increasing entropy.
Question?
Yes.
Does that mean that the assumed ambient conditions also include a humidity that is not equivalent to the, I forget what it's called, gas pressure? Or something like that?
Well, there's always that relationship. So that if we go back right to our vapor pressure chapter,
Pressure.
then you're always going to have some molecules that are, you know, not part of the liquid. So then there's equilibrium between that.
So do our ambient conditions always assume that the space above has 0 of the thing that is evaporating in this case?
You wouldn't make that assumption. There's no need to make that assumption. But you actually wouldn't want to assume that because there are molecules of water there, right? That's what the vapor pressure curve tells us. Does that make sense?
I'm just wondering what the assumed humidity would be then for the ambient conditions that things are considered spontaneous under.
I mean, you just assume 25 degrees Celsius, and then you could look up, right, the water vapor pressure curve, and that's generally what you're using. All right. And so another way to think about entropy then is basically, so we have this Q here, and I know it's shown here in big Q, but this is the same thing as little q that we saw, so that just means heat. So basically, you're saying, well, if we add kind of more heat than whatever temperature we're at, then we expect some sort of entropy increase. And then we can also see, so just like before with our enthalpy, our entropy change is, of course, our final entropy minus our initial entropy, and this would also be equal to, so we had whatever heat added over our temperature minus Q over our other temperature, that would also be equal to entropy. And then this gives us, so we could take out our Q, our heat added, and then we also get that our entropy then would just be equal to heat times our change in temperature. And so a couple of bookkeeping things and reminders. So again, from before, we said the first law of thermodynamics says energy cannot be created or destroyed. And then when we talk about energy, we're always looking at the system and the surroundings, and then of course the total universe. And since, right, the total energy cannot change, that means our change in the universe has to be 0. That means that, of course, whatever energy the system either gained or lost, these surroundings have to lose or gain the same thing. And so obviously, right, energy is just transferred then from one place to the other. And so now looking at the second law of thermodynamics, this says that the total entropy change of the universe must be positive for a process to be spontaneous. And so for a reversible process, then the change in entropy is equal to 0. For an irreversible process, then of course that means that your change in entropy is greater than 0. And so again, that's what's going to also be driving it forward is your positive change in entropy. And so if the entropy of the system decreases, then the entropy of the surroundings must increase by a larger amount, so either equal to or greater than whatever was decreased. And so again, when your system is negative, so it's becoming more ordered, and let's just add that, right? So if your delta S is negative, that means that we're getting a more ordered system, but somewhere we have to pay that price, and so then our delta S of our surroundings must be positive and big for a spontaneous process.
Positive and big. What do we define as big here?
And so entropy changes. So again, we can calculate this by looking at our final entropy minus our initial entropy. And entropy change is favorable when the result is a more random system. And so you probably just noticed that from your life, right? Your room tends to go towards chaos. And so obviously, right, the universe favors entropy. So anything that has a favorable, positive entropy change, that indicates that it might be spontaneous. And so changes that increase entropy tend to be reactions whose products are in a more random state. So we saw that, so if we go right back to our evaporation, so we started more ordered as a liquid, and now we're more disordered as a gas. And that makes sense, right? You have more movement. And so obviously solids are more ordered than liquids, and liquids are more ordered than gases. Reactions that have a large number of product molecules and reactant molecules. So we kind of saw that before with our reaction equilibrium and how we could kind of manipulate that. But that also has to do with order and disorder. So again, if you have more molecules, then you also have, right, more potential states where they can be at mathematically. And so that gives you more disorder. And then increasing temperature, that makes sense, right? That would also give more kinetic energy, and more collisions, so more disorder. And then again, like we saw with that dissolving of salt or really anything, so any sort of solids disassociating, so that goes again from ordered crystalline structure to now dissolved ions floating in solution. Again, we have our Q. So all we're saying, so this is back kind of from our thermodynamics. So again, our Q, whatever Q is gained also has to be lost by the other side. So the heat gained as one component is of course equal to the energy lost by the other. And again, that brings us back to this equation, which we can also change into work. So then this is basically saying how much work can we perform based on our temperature difference. And so again, this looks somewhat familiar. So again, quantifying entropy changes. So we said our entropy change in our surroundings is proportional to the amount of heat gained or lost. So going back to Q to signify heat. And again, whatever is either gained or lost by the system is opposite of what the surrounding does. And so the entropy change in the surroundings is also inversely proportional to temperature. And so at constant pressure and temperature, you have this overall relationship of your delta, your change in entropy is equal to, again, your change in enthalpy over temperature. All right, let's look at these examples here. And so take a few minutes and we'll go over them. So try to predict the sign of delta S for each of these processes. Yeah, so disorder is increasing. Oh, and then is the little sheet about like what question and what answer you want people to get from your Earth Day project still going around somewhere? Yeah, pass it around. Yeah, because I'm trying to collect everyone's questions on there. Because like I said, the Earth Club wants to make some like game thing with it. So, and again, put your partners that you're working with as well. All right, let's see what we got for these. So what do we think about A? So we're going from a gas to a liquid. What do you get?
This would be negative entropy for the system.
So negative. Perfect. Any questions on that one?
Yeah, I don't really understand why.
So there you're going. So you have to kind of think about either like in your head, you know, what the molecules are doing. So we know gas, right? They're floating around, they're moving. So that's a lot of entropy. Versus liquid, right? They still have some movement, but they're not flying all over the place. And then if you remember back, right, to these notes, it gave examples. So remember, right, solids are more ordered than liquids. So, and then liquid is more ordered than gas. So if you're going from more disorder to less disorder, then your entropy, so your like chaos, is basically decreasing then. So does that make sense?
Yeah.
So now try B. So solid carbon dioxide sublimes.
Positive entropy for the system.
So positive entropy. So again, now we go from solid to gas. So really ordered to disordered. And then what about C? What do we think about C? Go for it.
It'd still be positive entropy to the system because there's going to be more differences in the chemicals. There's two types of chemicals instead of one type of,
Yeah, or even just the fact that there's like 2 molecules of gas versus 3 molecules of gas. So that, just because we have 2 and then we went to 3, that means our entropy is increasing. You can also think, right, there's going to be physically more molecules, so now there's like literally more positions where they can be at. Good. Any questions on that? Yeah.
Maybe a little off topic, but would adding a catalyst to a reaction, would that make it still, would a reaction with a catalyst still be considered spontaneous, or would adding a catalyst be considered adding energy into the reaction?
That's kind of a good question. I think you could probably still consider it spontaneous, because then you're just like looking at this new reaction condition with your catalyst and like whether it occurs or not. And then the thing to remember with the catalyst, right, is it's just providing a new pathway.
Yeah.
And so that's what we've kind of talked about, is it's a whole nother reaction mechanism to
Right.
think about. So yeah, I think, yeah, then you could still consider it spontaneous after that. All right, so now we have our third law of thermodynamics here. So the absolute entropy of this substance is the amount of energy it has to dispersion of energy through its particles. And so the third law states that for a perfect crystal at absolute zero, the absolute entropy is 0 joules per mole Kelvin. So this is, obviously kind of a theoretical point since we're at absolute zero. And so therefore, every substance that is not a perfect crystal at absolute zero has some form of entropy. And so therefore, the absolute entropy of substances is always positive. And so now we'll have kind of our standard state conditions, again, like we've looked at before, and this is what our entropy is usually given in for these standard entropies. So I have a table on the next slide. And there's also a link to more entropies, so you can drive yourself crazy. And I'm sure your book has a ton of values as well somewhere, so this is a huge, complete list that I put a link to as well on the next slide. And so let's look at these standard conditions. And so for a gas, as you might imagine, this means that our gas is at 1 atm. For a solid or liquid, it's going to be in its most stable form at 1 atm of pressure and usually 25 degrees Celsius, again, for our standard conditions. And if we're looking at a solution, it's going to be a 1 molar solution. And so this should kind of remind you of enthalpy and how we calculate it. Again, same process. You look up your standard delta S values in a table. And so we said, again, for a process in which the final condition is more random than the initial condition, then our change in entropy should be positive. And then, of course, that means the entropy change is favorable for the process to be spontaneous. And so for a process in which the final condition is more orderly, then of course it's going to be negative, and entropy change is unfavorable, but again, that doesn't necessarily mean it won't occur. We'll summarize at the end how we've determined whether things occur or not. But then again, just like before, like we did with our delta H, we can find our delta S of our system by summing up our standard enthalpies of our product minus the sum of the standard enthalpies of our reactants. And so again, our standard enthalpies, this little circle afterwards indicates our standard state conditions. And so it's an extensive physical property. And so entropies are then for 1 mole of substance. Of course, it would change based on how much. And again, at your 298 Kelvin. And it depends, again, on the allotrope. So for carbon, you would have to look up, like, graphene. Let's see if we can find. I'm trying to search this thing. So here's at least one example. So you have benzene, right, liquid versus gas. I was trying to find, like, graphene versus graphite. All those would have different entropies. Oh, this has other stuff on there. Oh, here we go. So graphite versus diamond. So just all things to look out for when you look up these standard enthalpies. So blah, 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 standard enthalpy table. So again, usually given in joules per Kelvin. And so we can also look at our relative, entropic states. So again, a gas state has a larger entropy than the liquid state, so we could look at our standard table and see and compare that. So this one is saying for liquid water, it's 70 versus gas is 188. I'm just curious what this one says. Oh, that's enthalpy. I want entropy. Oh, no, entropy is over there, my bad. And so this one, pretty similar numbers. So again, expect discrepancies a little bit. So that one has 69.91, basically the same. But just be aware that will happen. And so here are just more comparisons of different gases. So we can compare. So we have a bunch of solids. So solids have pretty low entropy. So we have to look it up. And so the larger the molar mass, the larger the entropy. So that's at least a general trend. So we could see that here with hydrogen and argon. So slightly bigger mass, so 154. Or if we compare kind of our noble gases, so from helium to xenon, we can see a very steady trend of that increasing entropy. And so again, allotropes would make a difference since they're in different configurations. So the less constrained the structure of an allotrope, the larger the entropy. And so right with graphite, we know that those layers kind of shear off. So again, that's how you write. And so that, of course, means that they are not bonded together. So remember, with graphite, they're only held together by those intermolecular forces between them. So not an actual bond, so relatively easy to shear off. Compared to diamond, where we mentioned it's in that tetrahedral structure that gives it a lot of strength throughout. So now we're at basically what we are trying to get to this whole time, and that's Gibbs free energy. And this is basically the amount of energy that is available to do work. And then this is Gibbs is what's really going to tell us once we look and we compare, well, we need to look at our enthalpy, we need to look at our change in entropy, then we're going to look at those conditions, and then our delta G will tell us whether this will occur or not. So let's go through this. So again, delta G gives free energy, energy that's available to do work, and your process is considered spontaneous when delta G is negative. And so delta G will be negative under the following conditions, and we'll go through this. So of course, if delta H is negative and delta S is positive, well, that's good. So you are exothermic and also more random. So those are both favorable. It could also be negative as long as our change in entropy is negative, so exothermic reaction, and large. And then let's just say your entropy is negative, so becoming more ordered, but small enough so that, right, your change in enthalpy is good and kind of counteracts that. And obviously we're going to quantify this a little bit more, but this is good, again, just to go through. Or of course we could also have, if our enthalpy is positive, right, so an endothermic reaction, putting energy in, but it's small, but then our delta S is positive and large, so endothermic reaction, right, but increasing spontaneity. So that means that delta G can be negative, and this might also tend to occur at a high temperature. And so it will be positive under the following conditions, so then not spontaneous. So if we have our delta H is negative, and then we have a small change in entropy is negative and large, or again, high temperature, so now that's not favorable. So right, 2 ordered, so basically not going to happen. We could also have, so if delta H is positive, so again, endothermic reaction, and our change in entropy is positive, then that change in entropy may not be enough to overcome this, and so again, it would not occur, or again, low temperatures. And then if we have our delta H is positive, and then our change in entropy is negative, so this is never spontaneous, right? So if you have an endothermic reaction, but then your system becomes more ordered, that's just not going to happen. And then when delta G is 0, then you know your reaction is at equilibrium. And so here's just our visual graph. And so once again, right, we're looking at the Haber-Bosch process. Super important. So nitrogen plus hydrogen gives us ammonia. And so this is useful to think about since, again, this reaction has to be balanced at high temperatures and pressures to get it to go. And it's very energy intensive, again, from those high energies to get it to go. But we'll see, we'll kind of have the same idea before. We'll take our Q snapshot of it and then compare it to equilibrium and then be able to tell, is it going to be spontaneous? Is it favorable? Is it going to go? Or is it at equilibrium? All right, so let's get into the math a little. And so this is your main equation that you're going to need to know. And so I would write it down, highlight it, so this is relevant. And so again, Gibbs free energy is the maximum amount of work energy that can be released to the surroundings by a system. So again, that's work that's available. And so we see that Gibbs now combines entropy and enthalpy. And it can also be referred to as chemical potential, because again, it's what's available to work. And so our delta G of our system then is equal to our change in enthalpy of our system minus the change in entropy times the temperature. And because our change in entropy of the universe determines whether a process is spontaneous. Delta G also determines spontaneity. And so if our change in entropy is positive when spontaneous, that means, of course, our delta G is negative. And so I like this table a lot. You know, this was a little wordy in some senses, but this table gives a really good summary of when things are going to be spontaneous, not spontaneous. And so if you look, right, it just gives you kind of a rundown. So again, if your reaction is exothermic then, but has an increasing entropy, right, that's going to be spontaneous at both low temperatures and high temperatures. And it just gives some example. And so that's going to be N2O disassociating. Yeah, question?
What is the H one? Was that from last time?
Yeah, so remember H is still enthalpy. Yeah, and then, so going back, right, kind of a quick refresher. Oops. So, right, this chart that I linked to has enthalpy, gives you Gibbs, and also entropy. So you can calculate Gibbs given your entropy and your enthalpy. And right, so you kind of remember from before how we did our change in enthalpy. It was just the same thing, you know, the products, the sum of the products minus the reactants. It's very similar. So just like, right, this formula was for our delta S, we had the same thing, right, for delta H, where we said, right, we take the sum of the heat of formation of our products, subtract it by the sum of the heat of formation, right, of our reactants. And that's how we got our change in H, which again was related to exothermic and endothermic. And so the same thing. So now, right, Gibbs is basically putting it all together, which you can come up with some fun problems where you have to calculate the delta H, the delta S, and then determine delta G, basically. So putting it all together. But then, again, we can follow along on this chart. So if our reaction is endothermic, so needs energy, right, with our delta H, but then has a decreasing entropy, so more ordered. Now this is saying this is probably non-spontaneous at both low temperatures and high temperatures. So your delta G is always going to be positive. And so we can see one example of this would be oxygen going to ozone. And so that would be a non-spontaneous process, so that doesn't really happen. Otherwise, again, we'd be breathing in a lot of ozone probably. And so we can see, right, if something, though, is exothermic and is more ordered, that's going to be spontaneous at low temperatures. But then once we get to high enough temperatures, right, where this now overwhelms our change in enthalpy, then it will be non-spontaneous. And so something like that would be, of course, water going from liquid to a solid. And so that makes sense, right? You know that it's going to occur at a low temperature, so obviously probably below the freezing point, and that process will occur. But then again, at high temperatures, obviously, your liquid is not going to go back to solid at high enough temperatures. And then, of course, our last scenario was if we had something that's endothermic, but then also increasing entropy. And so that means that it would be non-spontaneous at low temperatures, right, from that positive delta H there. But then since we have this minus temperature times our entropy factor, as long as we got to a high enough temperature, then that positive change in entropy would be enough to overcome that endothermic need. And so one example, again, is now liquid going to gas. And so we know that process does occur, and so that would probably have to occur at least above 0 degrees Celsius. Questions about this? So this little part right here is kind of like your cheat sheet, I think, for this chapter, because we got this reaction, and then we got our, little handy chart that helps us kind of summarize everything. All right, so now let's see if we can put it all together. So now we're looking at this reaction for the decomposition of carbon tetrachloride gas. And so carbon tetrachloride can decompose to carbon, which is given in the graphite form, plus 2 equivalents of chlorine gas. And so it gives you the delta H and delta S. And so it says first calculate delta G at 25 degrees Celsius and see whether it's spontaneous. And then if it's not spontaneous, determine what temperature, if any, it would be spontaneous. And of course, before I let y'all loose, what do you need to do first with this temperature? What is our temperature always in? Convert to Kelvin. So excellent. Don't forget that. That's always the key. So I'll give y'all.
Is it plus 232?
Plus 273.
What's the formula for G again? Okay. That's H1. Thank you. You should probably scroll that down further.
So did we get an answer yet? So some tricky things that hopefully you were paying attention to is, of course, the units. So, right, enthalpy tends to be in kilojoules just because of the numbers. And our delta S tends to be in joules, again, just because of the changes or order of magnitude. So just watch that. And so I'll go through this setup and hopefully someone can tell me a number. So I have delta G. I'm just rewriting the formula for a second. And so we said we had to convert to Kelvin too. And so I'm going to leave my delta H in kilojoules. If you wanted to convert it to joules, that would also work, but I'm going with converting everything to kilojoules route. So minus what is that, 298 times our S, so just again, convert that to the appropriate units. And so what do you get for your delta G for this reaction? So 53. And that's in kilojoules, right? Yeah. And so looking at this, so is it spontaneous? What do we say? What did delta G have to be spontaneous? Other way.
It has to be negative.
So it has to be negative. So write that somewhere too, right? Delta G has to be negative to be spontaneous. So is this spontaneous?
I have a question.
So no, not spontaneous. Yeah, question?
Why are we, if it was joules per K for delta S, why did we put where's the K?
K is going to be factored out times your temperature. So this per
Okay.
Kelvin times Kelvin.
Got it.
So then see if you can do B now. So where is that line, if any, that the reaction may become spontaneous? So what would that be mathematically that you should try to set up?
Algebra problem.
Do you have an answer?
Yeah.
Oh, let's give people another minute or two. So then, how do we need to set this up? What did y'all plug in? Yeah.
I just times the temperature by the change in entropy, and I got that it should be less than 42.375 kilojoules for your delta H.
Well, we want to figure out temperature though, right?
I have it.
Yeah, because we have, so what do we need to set up first of all? So just like tell me algebraically what we should set up.
95.7 minus x times
Yep.
0.1422 and solve for x.
Let's go, before we get to there, like more simply, like what do we need to solve for, like what do we need to plug in for G, or what are we trying to find?
We're trying to find the temperature, so set temperature to x.
Right, but what does G need to be? Negative, right? So we at least want G to be less than 0, right? So it's easiest, let's just set G to 0, because that's going to be right where that threshold occurs. And so that just equals to delta H minus Ts. And so now, I think what you were saying, so we get just plugging that in. So that 95.7 then is equal to our, whatever our temperature is, times our delta S. So that 0.1422. And so now we can solve for temperature. And so what do we get for T then?
672.996. probably safe to just round up to 673 because we need it negative anyways.
Yeah, so 672, 673 Kelvin, something like that. So did we all get somewhere around 672, 673? Excellent. All right. So now we're looking at kind of the last bit here. So of course we said delta G of our reaction is 0 at equilibrium. And so now this is relating back to K. So we said delta G is equal to negative RT times the natural log of K. And I think R is going to be our gas constant. So R is at 8.314 joules per mole Kelvin in this case. And so when K is less than 1, G is going to be positive and the reaction is spontaneous in the reverse direction. If K is greater than 1, then delta G is negative and the reaction is spontaneous in the forward direction. Then of course, if delta G is 0 and K is 1, then the reaction is at equilibrium. So blah, blah, blah. And so since our sign of G determines whether a reaction is spontaneous, we expect a relationship between our delta G of our reaction and then our heat over our equilibrium or our pressure constant over our Kp. And so our relationship is our delta G of our reaction is also equal to RT times the natural log of our heat over our Kc there. So our equilibrium expression. Or if we're using gases, then of course same thing, just with the pressure applied. And since our units are the same, then that just gives us a unitless ratio there. All right, so let's look at this one. And so it says, use our tabulated free energies to calculate our equilibrium constant for the reaction at 298 Kelvin. And so we have this equilibrium here. So see if you can figure this out and then. Oh, so R is at 8.314. And we have our T. And we're given our delta G's of formation. So at least start with that. See if you can calculate your delta G for your reaction. And then we'll go from there. So are people confused or? So we're trying to solve for K, right? Maybe we should go through this together. Sorry, I just see like blank faces. So it says, right, use our energies here of formation to calculate our equilibrium constant. So let's go through that together. So let's just rewrite our formula, right? So we said that delta G of our reaction is equal to negative RT times our natural log of K, with K being our equilibrium constant, just like before when we talked about equilibrium way in the beginning. And so they gave us our delta G's, right, our standard delta G of formation. And so just like we can do with enthalpy and entropy, we can find our delta G of our reaction by doing, right, products minus reactants again. So the sum, right, then of the delta G products minus the sum of the delta G of our reactants. So then the trick, so we have two, right, two equivalents of our nitrogen dioxide. So we're going to have to do 2 times 51.3 minus then, so there's only one, so 99.8. And so let's just do that first. And I didn't pull up my calculator. So now we just have our delta G. So this is 2.8, and then just watching my units, so kilojoules. And so now it says, right, so now we can plug this into our formula. So we have R, we have T, we're trying to solve for K. And so now let's do that. So 2.8, and I'm just writing my units so I don't get confused. So kilojoules is equal to, I already have an issue. So what's the problem with our R versus our G? Exactly. So I don't want to change my R. So I'm just going to change this then to 2,800 joules is equal to negative. So now my R, 8.314 times T, so that we said that was 298 Kelvin. And that matches up with our R unit, times the natural log of K, which we're trying to solve for K. And so now it's just some math, so let's plug in and divide. So divided by negative 8.314 divided by 298. So I get negative 1.13 is equal to the natural log of K. And so where do we go from here? Do you remember how to get rid of natural log? Yeah, I just didn't remember what E was. Good job. Oh. So now take it to the power. So E to the power 1.13. So we take everything to the E. So E to the natural log gets rid of that and gives you K. And then E to the negative 1.13 is apparently that. And so that then is our K. And so now that, right, this would be your equilibrium constant. And so now we related everything back to equilibrium and all that fun. I'm actually shocked we made it through most of the chapter. So this is the last little bit So Y is the equilibrium constant, temperature dependent. So if we look at these two equations, then we can get that our natural log of K, so our equilibrium constant, is equal to our delta H of our reaction over R over T plus our entropy over R. And so now this would give us something fun that you could do in lab. So then if you were to graph the natural log of K versus the inverse T in a straight line, you would get this is equal to the slope. So of course you could calculate your delta H, right, by multiplying your slope by R. So of course that would get rid of it. Solve for H, and then your y-intercept would be equal to your entropy over R. So again, just multiply by R, that 8.314 again, joules, moles, Kelvin, and that gives you entropy back out. So that's useful. I wouldn't be surprised if it cropped up in a lab or something. I see what happened. So we made it through the notes, but we did not do practice problems. All right, so we're probably going to have to end here for the day, just in interest of time, and also that fire alarm is going to go off at 1. But I will say, so homework is at the front, and then if you have questions about this, you can also bug Dusty on Thursday. So Dusty, right, he's our resident physicist, so he understands all this stuff. He can plug into chemical equations, and so if you have questions, you can ask him. I'm also available. So again, the fire alarm's probably going to go off, but if anyone wants to come back here afterwards, we can go over stuff. Or Isabel, I know you had questions, so we could do that outside too with the fire alarm. All right, so I'm probably going to end here for the day. And again, ask me questions, email me for appointments. Oh, and then we should chat. If you need to chat with me about needing materials, we should do that before the fire alarm goes off, and then I won't be able to find you. Oh, yep. Did everybody fill this in? Is there other copies of this?
I had
Oh, sweet. Oh, yeah, go for it.
2 questions.
Thank you.
So I think I mentioned that we would need activated charcoal.
Oh, yeah, we'll
and I
have to check with the stock room on that.
Okay, it's not, we're gonna be mostly using sediment anyway, so it was just like so this would be nice, but it's not needed, thing. And then can you, run through what why I got points taken off, just so that I can improve and better understand?
Did I? Yes, okay. So you did base over acid. So I think it's just like a little error here. I wasn't even quite sure myself. Because, right, you need to put the log of base over acid. I can't quite read those numbers, but it looks like you did 0.005, which
Yes.
is correct for the base. And then it should be 0.0015 for the acid.
Oh.
And I'm not quite sure what happened,
Maybe
or maybe, because it looks like you put 1 in molarity, but maybe you didn't put this in molarity, and that's what got it messed up.
Yes,
Yeah.
I think this was in molarity.
Yeah.
This is not.
Yeah.
That is what I got wrong. Okay.
Very minor error, so yeah, I only took
Okay.
off half since you had the right idea.
Okay.